Okay, so quick review here, slope and straight lines basically. Calculus is the study of graphs. Essentially, we are looking at slopes of graphs in the calculus we do. The next type of calculus that you'll see next year, I assume, would be integral calculus, and it's looking at the area underneath graphs. So basically, talking about slope, I'm sure you remember hearing the idea that slope is rise over run. And just going to quickly say, if you don't remember anything here, don't hesitate to ask about it. It's been a while, but the concepts certainly you've gone through. And again, it was quite a while ago. So if we're looking at this graph off to the side here, just as a kind of starting point, this point is -4, 0. This point is 0, 6. And so as I move across my graph going left to right, from here I am going to go up 6. You have to rise a distance of 6. And I have to run a distance of 4. And so my slope is 6 over 4, which reduces to 3/2. Okay, so that's sort of the definition of slope. If we're looking at a question where we have information instead of an actual drawn graph, -1, 6 is one point, -12, -4 is the other. I'm not too concerned about where they are, although if I kind of picture them, I recognize that Q technically is more to the left, and probably if I thought about it this way, I would consider that my point 1 and that my point 2. Q would be my point 1 and P would be my point 2. That doesn't matter though. I can work this in any order I like, because really all I'm doing is dealing with the math behind it. So the slope is going to be my y2 over my x2. So again, I'll choose this to be my y2 and my x2, although if I do it the other way, I will get the same answer. And so my y value is the 6. Always, when we declare a point, we declare the x value first. So it's 6 over the -1 minus, and I'm going to suggest right off the bat, and I always suggest it to all my students, anytime you're doing a substitution, use brackets. The first one I probably should have even put in brackets just to kind of keep my rule. But what I want to do is avoid having confusion about the minus and then minus a negative or something like that. So I have a negative value here and here. Sorry, I have a subtraction here and here. I'm going to have y values, y and x values here that happen to be negative as well. And so, of course, -4 is my y, -12 is my x. And now I've got 6 minus -4. I'm taking away negative values, which means I'm going to get more positive. Here again, -1, I'm taking away the negativity, and so I'm becoming more positive. And so my slope here is 10 over 11. Second question now. Another thing that we need to be able to do, or want to be able to do, is find an equation given some information. So we can assume the original question was actually this, and the first thing we did was we went about finding slope. We need that anyway, so it works out just fine. Here I have y equals mx plus b. B is the y-intercept, in case you've forgotten that. And if I knew that value right off the bat, and I knew my slope right off the bat, I could write my final equation immediately. I don't, so I'll have to find that. So what do I know? I know that I have y values from the previous question. I have a slope. I have x values from the previous question, and I'm looking to find the b value. So my slope here is the 10/11. I picked really ugly numbers. My point, my x, y value can either be this as a combination or this as a combination. Again, I'll get the same answer if I don't make any mistakes. One might be nicer to work with than the other sometimes, and so I'll pick the nicer one. In this case, I don't think it matters too much. This is a little bit nicer, I guess. So 6 is my y, and -1 is my x. And so I have 6 is equal to 10 elevenths times -1, negative 10 elevenths, plus the b value. Now I need to isolate b, so I'm going to add 10 elevenths over here. 6 plus 10 elevenths is my b value. And in order to add these, I want a common denominator, so I have 66 elevenths. Multiply top and bottom by 11. Numerator, denominator, and numerator. Sorry, numerator and denominator in that order. So b is going to be 66 elevenths plus 10 elevenths, which is 76 elevenths. And so my equation is y is equal to 10 elevenths of x plus 76 elevenths. Ooh, that was ugly. So again, just going through these quickly, they are all review for sure. Didn't leave myself a lot of room for this question, but complete a table of values, integer values for -3 through +3. I won't do them all, but just kind of, again, showing how we would go about doing this. Let's change that. So typically, you do a little table of values. X is on the left, Y is on the right. And it's suggesting the values from -3 to +3. If I'm doing this without these specific instructions, of course, I'm going to pick values that I want to use. We won't be graphing something like this with a table of values, but again, the idea of being able to substitute an x value into an equation, solve for y, that becomes important. So this is just kind of previewing that idea. So if I'm using -3, I have, I can kind of do this off to the side, 2 times -3 cubed minus -3 squared plus 4. So this is going to be my y value. If I can do this in my head, great. If I can't, then I could kind of write it down off to the side and just fill in the value, or pick up a calculator, obviously, as well. This is -27. Okay, so -3 times -3 is 9, times another -3 is -27. Again, pick up your calculator. I just don't happen to have one here. -3 squared is +9. And so I've got -54 minus 9 plus 4, the plus sign. And so y is, this is -63, yeah, so -59. -63 plus 4, actually, if I look at it again, -54 plus 4 is -50 minus 9, -59. And so that becomes 1 point on my graph. So if I am going to, if I were going to draw this, I have my nice piece of graph paper over here. What a nice piece of graph paper. Thanks. And I count across -3, 1, 2, 3, and down to -59. Oh, look at it, just fits right in there beautifully. Of course, on a piece of graph paper, you'll do a much better job than I am right here. And then go ahead and find -2, plot it, and you find that the graph looks something like a cubic of some sort, because it is a cubic of some sort. Okay, so those are sort of the things I wanted to cover. A couple of definitions here that become important, and we should remember the word domain. As soon as you see that, it means basically tell us what all the possible x values for the relation are. So it can be a graph, it can be an equation, it could just be defined in some other way, I suppose. Those are the main things you'll see, though. And so if we remember sort of proper form, we do something like x, oops. We can declare that the domain is equal to x such that something like -2 is less than or equal to x is less than 10,000, where x belongs to the real numbers. There's something like this. I can't even remember how to do it. It doesn't really matter. The point that I was trying to make was the important thing, or what I was going to say was the important thing is this. Okay, so if you know what the values of x are, this is sort of how we'll write it. If it is all the values of r that we're interested in, then just this becomes our answer. Don't worry about being too fancy with this sort of thing. As you can see, I'm missing something here. I think it's just a comma, but I haven't written a domain that way in many, many moons. When you get to university, your profs might care a lot. I notice a lot of the textbooks don't even use quite proper syntax this way anymore. So knowing that this is the answer, those are the values of x that are legit, that's what we're looking to do. Range, same sort of thing, all possible y values for a relation. A function is basically any relation where x has only one. Has only one. Okay, that's fine. X has only one y value. Okay, so, and we call the vertical line test as, or we look at the vertical line test as a way of defining that. So pretty simple. I have a graph of some sort, and it's all fancy dance. Ooh, look at this. Oh, look at, I can't believe how fancy I am. And we can just draw a nice vertical line. And essentially, if that vertical line only touches the graph at one spot all the time as we move across, we have a function. Mathematically speaking, basically as long as when you plug x in, you get a single y value. So if you look at what we did here, when I put any x value in here, I always get a unique y value. Then I have a function. I think everything we do this year will be a function again. I won't promise that just off the top of my head, but things like circles, obviously not functions. Things like parabolas turned sideways, rotated parabolas, not functions. But I think everything we run into will be. But as long as you can sort of keep that in mind, if you can see that a vertical line cuts the graph in two spots, that it's not a function. Or if you can figure out when I put x in, I get either 3 or -3 as my solution for y, then it's not a function either. I thought of something else I was going to say. I don't know what it is, so I will stop there. I remember what it was. So last kind of quick comment here, dealing with domain. Essentially for us, there are a couple of different things that we have to avoid when we're looking at domain. And you want to remember with domain, all I'm looking to do is say, can I put this number into my expression? Can I put a 6 in here for x and get a legitimate answer? Yes, I can. So a couple of keys for domain specifically. The things we want to avoid for domain are division by 0 and negative numbers inside of square roots. That was actually a bad example because, of course, if x happens to be a negative value there, then that is perfectly legitimate. So something like this is the problem. So domain actually is pretty easy to figure out usually. You're looking for x values that give you negative square roots, and you want to say that those are not allowed. You want to look for x values that give us division by 0 and say those are not allowed. And pretty much those are the only things we look for. Okay, so that was the end. That was the last thing I wanted to talk about.